Alrighty, happy Tuesday. We're moving on to our maps and hash tables. This is actually really interesting. This is another way of storing data. Again, it's all about the trade-offs of what's fast and what's slow. So far we've looked at most of our performance was O of N for a lot of operations, not everything. And we were able to get some faster speeds on some things on average, right? If we amortize that across for our arrays. When we looked at our linked list, we said, okay, we can always add super fast if we know what position we're at. That was cool, but you have to get to these positions. That can take a little while here. Then we looked at trees, specifically binary trees, and then priority queues. We said, okay, well, we can add stuff in. If we're in this tree structure, this heap structure for a priority queue, at most we'll take log of n, which is pretty good, right? Because n doubles really quick. Right, so the log works out pretty well for putting things in some sort of sorted order, but that's not unordered. Right? If we want some sort of unordered list to be able to get things out, see if I have the value or get the value associated with some sort of thing out really quickly, that's what we're looking at the map and the hash table for. So the map says, hey, here's a key, here's the associated value. This is our Python dictionary. We've done these a lot here. So to store those quickly, we're going to take advantage of this idea of a hash table, which is pretty cool. So remember, when we use dictionaries, they're not sorted. There's no guarantee of order. And what we're going to see here is why there's no guarantee of order in a second. So let me fire up PyCharm and do a new project here. Oh.
Can I turn the lights off?
Yeah, please.
Is it there?
Oh, I've got some here. Let's see. How's that? Is that better? All right, yeah, no problems. This is week 11. 11 hash maps. Essentially, we'll do a hash map.
Is that still the third lab?
I'm sorry?
Is that the third lab?
No, I was working on grading project 1. All right. Now, we need to go pull this up in our downloads real quick. Data structures. So there's some specific ways that maps implement these functions, which is really cool. So we're going to look at these maps and dictionaries. Again, I love how he likes to use composition or inheritance and build off of things here, but it's a lot of trouble for us. So we could define these functions here, right? If you give me a map and give me the key, I'll give you the value associated with the key. That's what our dictionary does. You can assign to it, you can delete it, you can get the length, and then iterable, we'll talk about later how we can iterate over them. We can say if there's a key in the given map, we can get, which has a default value. So the benefit of this one, remember when we used dictionaries, was we could always get something back out. You wouldn't just crash if you didn't have the key error. So defaults are pretty handy. So we don't get our key errors. You could set defaults if you want. You could pop a given key out. Lots of options here. Get just the keys out. So figuring out how to build one ourselves here gets to be a little trickier. So our map base. So he uses this map base class. Again, all sorts of fun things. It's okay, right? We're not going to do all of them. You can look more at these ones later. So we are going to use the hash map. You can do an unsorted map, you can sort, you can later with all these other structures. Really fun. It's just a lot, right? So we're just going to try and do something a little bit more basic here. So you're going to have inside of your map is an item, a private class for item that has your key and your value. Okay, this way we can store keys and values, but this way we have a class that represents them here. Let's write our class for hash map here. Oh goodness, that was a lot of quotes. We're also going to have that class for item or underscore item, mark it as private.
What have we been working with nested classes? What is the point of nested classes?
So this is an implementation detail that I don't want other people to know about. So when we talk about that idea of abstraction, I'm going to hide or encapsulation. I'm going to put everything into one nice little package and an abstraction where they just get my public interface, the public functions.
Right.
They don't ever need to know what this item class is. It only exists for my implementation so that I can use it inside of the class. I'm never giving anyone item. When we did positions, that became a little bit public because I wanted the user to work with positions. But with nodes, I never gave them a node. He said, hey, node's going to be my private detail here. This is how I track things. You can use a position. Here's the position class. But these are private details.
That's why I have like the big class linked list, and within it to have the class nodes.
Yeah, that's just a detail of how we wanted to track it here for ourselves.
But could you still be able to do the same thing without the bigger class? Like without the HashMap class, can you still do that all?
We could make a class for item, but this way it makes it like part of HashMap and private in HashMap. Yeah, wouldn't necessarily have to be, but that's just a little bit nicer. So we'll say key and then value. We can say value's none, unless you tell me otherwise. It's probably fine. Self.key is the key. Self.value is the value. Remember that we looked at one time way back when you could use a dictionary without associated values. I think it was essentially a set when we talked about these different structures. A set is really like a dictionary without associated values, because you get a unique set of keys. So if you only give it keys, great, now you have a set. That's all. So we have these items here. And then items, yeah, we can compare keys, sure. So define equal, return self.key is equal to other.key. And then not equal, return self, not equal, not self equals other, and less than. Okay, sure, so we can compare a less than. So if we wanted to do some sorting, we could use a less than. Return self.key is less than other.key. This is where we can sort these keys out if we want to sort the keys.
Instead of return not self versus other, can you also use return self different from other?
Well, so this is the not equals. So if you say self not equals other, it would call this function again and call this function again and call this function again. We'd be stuck in an infinite loop. Right. We're using the equals from this one that we did right. Notice it like highlights it for me when I'm clicking on this one.
So if it's not equal.
Yeah, so we say check the equals and then flip it, say not. Yep. So like I think that's why they had the parentheses in his, just to show that that's in here. Okay, so we've got our item class, and this will let me store keys and values. The slots thing is fun. It speeds up performance. We don't care. It's not worth it for our purposes here. And then different ways of doing this here. If you wanted to use an unsorted table map, again, this feels a little silly to write a terrible one. We kind of did that with the queues, but it just gets to be a lot with this. So if you're an unsorted table map, you just throw everything in a list. And then you have to go find that value in the list everywhere, every time. So if you think of performance for this, it's probably not very good, right? The more n I have, the more things I have to look through in my table, my list, right? So I think right off the bat we can say this is probably not going to be a very fast solution. But in classic book form, he gives you the bad one first. So we're going to skip that. So we're going to use a hash table instead. So a hash table is a fancy way of storing stuff here. So we're going to define our init here, init, and then we'll have a self dot hash table is a list. And now with my list, I want to throw a bunch of things in here. I'm going to oversize my list to start. This is one of the things we're going to do with our hash table. So I want really none, I think what, times 10, or there's really cool math around all this stuff. If you use prime numbers, it works really well. 10 is actually not a very good number for this, I apologize. So like 11. People have looked at ways you can speed this up. We're not looking for like the most possible performance of this. We're just looking at something a little bit better, okay? So we'll just use 11 and we can recognize there are better ways. I'm sorry?
What exactly are we going to use this for?
So we're going to store values in this hash table so we can see how we can get really quick lookups for values, really quick lookups.
So why was it not times 11?
So this should give me 11 nuns. So I want 11 spots in this list. So I want to have a bunch of empty places so I can start putting things in. Prime numbers are good. And something bigger than like 2 to start.
Is that a list?
Yeah, it's just a list. So it's a list of 11 nuns. So none.
It's one list with 11 nuns?
Yeah.
Never seen that before.
I think we did this way back when we started our array-based lists. I think I was a video lecture because I think I was sick that day or something. Just a way to start a list of a certain size.
Okay.
Yep. So we got a lot of spaces here. So we set up the hash table, and then we have our number of items. Self dot number of items is 0. Now I can start throwing things in here. Now, there's actually a function here called hash. This is a built-in function. So one of the cool things you can do with objects is you can generate a hash value of it. So if you've done anything with like cryptography, and you might not have, and that's okay, a hash value, it's sort of like a one-way encryption. It's generally what we consider those to be. So a hash value is just a unique value generated by this. You're not supposed to be able to decode the thing, you're just giving a unique value for something. So we use hashes in encryption a lot to say, hey, when you go download a file, here's what the hash value should be. So that if you get this value, when you check this, you know that no one else has intercepted this file and modified it, which is generally pretty useful. Right? We don't do it automatically. There's stuff behind the scenes that can check those sorts of things too. But you'll see a lot of download sites say, hey, here's the hash for this. So it's a nice one-way thing. When we store passwords in systems, we store hashes of passwords. No one should store your actual password. They should store this hashed version of the password so that they don't even have access to what it is. Right? It's just a nice way to do some protection. And there's all sorts of unsecurity things around it. But that being said, hashes here are a way to generate a specific value out of any object. So, and there's some little notes here. It says 2 objects that compare equal must also have the same hash value, but the reverse is not necessarily true. So we'll just think about that for a second. So now doing like strings and integers, probably pretty easy, right? So the string Eric, if I generate a hash value for it, should always be the hash value for the string Eric.
Will always be the same.
Always be the same. So a hash is a static function, doesn't change. It will always generate the exact same value every single time. The hash value for 7 is probably 7, right? If you just like hash value of integers, I think those are pretty boring here because it's already a pretty unique number. It's really easy. Yeah, it's 7. Okay, so nothing really interesting here. But like 2.4, we get a hash value of 2.4. Now we get, I don't even know what that is. That's a big number here. Okay? So it's some integer value that you're going to get back here for a given value, for something. Now, if 2 objects are equal, they should have the same hash. But just because you have the same hash doesn't mean you will be equal objects. That part is going to be important. So now this doesn't come up with our basic types, but when we start having classes, we start having instances of classes here. So we wrote a class for like score, or I don't know, assignment, right? Assignment. We said you're going to have a name and a score, something like that, right? So self.name equals name and self.score equals score. And we can make an assignment like, I don't know, first quiz equals an assignment, quiz 1 and 10. We can print the hash of the first quiz. There's the hash value for first quiz.
So the hash value basically, like, it's just a number to represent it.
It's a number to represent it, yep. And if you don't generate one, you get one built in for you. This is a built-in function. So remember, everything is an object in Python. So there's a couple of functions we get by default. So everything can hash. So I can make a second quiz here for quiz 1, same thing here. But if I print the hash of that one, I'm going to get a different value.
Like
Ever so slightly different value. I'm sorry?
It's the hash of the value of the object instance first quiz with values quiz 1 and 10.
So the values inside here don't actually matter at all right now. So because we didn't write our own hash, what it's going to do is use your memory address. That's why these are really close. This is essentially your memory address.
So that's the only, the number is relative to the object itself, not to the values it has.
For now, until we tell it otherwise. So when you write a class, it doesn't know how to hash it. So it has to use the objects version, which is your memory address. Right? So
how come when we put hash 7, give exactly 7 for these?
because it's an integer. So hash have to be integers. So to generate a new unique number for the number 7 is just a lot of extra work.
So whenever you put a specific like, number to give you that exact same.
So you say it again?
Whenever you put like a specific number, like 7, 10, or any number for the hash, it's going to give you that same number.
For integers, yeah. Yeah. There's no extra calculations you have to do, but objects get trickier. So now if we did something like second quiz equals the first quiz, and we printed the hashes of them here. Now we get the same value. Right? Remember, when you take one object, assign it to another, you have two variables pointed to the same place. When you hash them, they are the same place, the same memory address. Right? So if you don't define a function for hash, you're just going to get what's its memory address. But you can define a hash function. You can define hash. So hash should return a value that is a unique representation of this, name and score. So for our purposes, we can return maybe hash of self.name plus hash of self.score. Something unique here, right? Sure. So now these two should come out to the same hash because they have the same values, and we're using those values to generate hash values.
What's the difference of doing it?
So we're writing our own way of doing it. So instead of saying, hey, what's my memory address? We're saying, hey, take my name and score, take those hashes and add them together.
Because otherwise we'll just be creating the hash relative to the object.
Just the memory address. Yep. So this way now I can make equivalent objects have the same hash value. This is what we want. You want objects that should be equivalent to have the same hash value, right? When we looked at hashing, it says two objects that compare equal must also have the same hash value. So we didn't add an equals yet, but we should add an equals, right? To compare if two assignments are the same, we're going to return self.name equals other.name and self.score equals other.score. So if first quiz and second quiz are equal, they should have the same hash. So if we don't write this hash function, we've done a bad thing, right? Because they're comparing equal, but they're not hashing to the same value. Now we've done this stuff before, we never really worried about it. But what that means is we can't store it in the dictionary. I think we did that once, right? So now I have an equals here. Unhashable type assignment. Notice it didn't have that before we had an equals in here. It hashes just fine. If you add an equals, now you can't hash it.
Why not?
Because hash says if you compare equals, your hashes must be the same. So Python is saying, if you've added equals, I can't hash this because you don't have an implementation for hash. You can't use the object one because you're going to compare equal, and the hash calculation is just based on memory address. It won't say they're equal. So by having equals, you can't use hash until you write your own hash. Because it wants to ensure that rule that if two instances are equal, then they have to have the same hash value. There's no way to do that unless you write your own hash function, once we've written an equals function. So Python can track that behind the scenes. And this sort of thing, right? If we wanted to make a dictionary here, we can't use these as keys. So like here's my, grade book equals a dictionary of first quiz, right? Colon, 10 or something like that, right? Some sort of value here. Sorry, I don't know what that number is. I keep getting spam calls. It's election season, right? Let me take out these hashes here. Sorry. Oh yeah, and it still gives me the same error. Unhashable type assignment, right? You can't put it in a dictionary because it's unhashable. This is a new error. We've never seen this unhashable type before, unless you tried to use our custom objects in dictionaries. They can't be keys because you can't hash them. Because behind the scenes, Python uses the hash value in dictionaries to create these hash maps. Hash maps are super fast and fun.
So a class object cannot be the key?
Unless you have a equals and a hash function.
That's so confusing.
Yep, we've never tried it before, so now we're learning. Hey, you can't do this sort of thing. So the reason is, right, we need our hash function here. Turn hash of self.name, hash of self.score. Right, so now we can, because I can generate a hash value. Now I can do these things, because I've told Python, this is how you calculate a unique hash value. or a consistent hash value, right?
So that's creating the hash value of the gradebook.
I'm sorry?
What you just did with that hash is creating the hash value of the gradebook.
It makes it so you can create a hash value for an assignment. So if you can have a hash value and you can have an equals method, then you can use it in a dictionary, right? Without those, I don't think we can add it. Oh, it does let it add us to a dictionary with neither, but you can't have one without the other, right? Oh, okay, no, I'm sorry. So you can have hash without equals, but you can't have equals without hash in the dictionary. Silly rules, it's okay. Don't worry too much about it. Now, all of that to say, well, why is that the case? So what we're going to do with our hash table is we're going to generate the hash value of the object that you're going to put in here and stick it in that location in my list, in that index. So to go and add an item here, hang on. I always have to go look these up. I can never remember what the syntax is for these. Where is it here? Oh my goodness. Just give me the code. Get item, there we go, set item. Okay, so for set item, there we go, for a key and a value, set item. Set item. For a given key and value, right? So to set the value of an item, this is either add or update, right? We're either gonna add the key and value, or we're gonna find the key and update the value for this one here. So for a given key then, I need to generate the hash value and see where it should go in my hash table. Right? So the index is going to be, so it'll be hash of the key modulus the length of my self.hash table.
What exactly does set item do?
So when we like use a dictionary and you say, hey, gradebook, key of Eric equals 10. We're setting, here's the key, here's the associated value. This is the set item here. So we can use our hash map, our, custom.
Now, waiting to like gradebook Eric equals to 10, we're saying that within gradebook, Eric will be your value.
Key, this is the key, yep, and this is the associated value. Right, so that's the set item, once we wrote set item. So I need to find where this should go, is the idea here with this. So the index is going to tell me the hash of the key modulus the length of my hash table. So if I have 11 spots, I'm going to find which spot this one is in of those 11 and see if it's there. Right? If it's not there, I can add it. If it is there, now I can go update the value. Right? So I'm going to take my hash table, so see if it's none. So if self.hash table at the index is none, then I can go add it. Right? I can say self.hash table at the index equals item, so self.item given the key and the value. Right? Go set it. That should be fine. That's weird.
So why don't we say .length?
So we don't want to be adding it to the end of our hash table because we want to say, hey, I've got 11 spots here. I'm going to start throwing things in these spots. And really what we want to do is we actually want to create buckets. Here I'll picture here. This is the bucketed idea. This is the best way here. So if I have 11 buckets, or let's do like 5 because that's a little easier to draw here. 5 buckets. So this is my list here with indexes 0, 1, 2, 3, and 4. Okay? So any value you want to give me, I can generate the hash of the key, modulus it by 5. I'll get a value 0, 1, 2, 3, or 4. So if you want to throw out some values here, right, we can start throwing them in the bucket based on where they hash. So maybe Eric hashes to 1. So we get Eric and 10 or something like that. Here's the key value pair, right? And maybe we do Jeb, maybe Jeb hashes to 2, his value is 7 or something like that. Maybe VV hashes to 1. I don't know what the strings are going to hash to because I only have 5 spots here, and maybe you get for a score of 8. So the idea is, what we can do is no matter how many items I have, I can generate the hash value instantly and find out what bucket it goes in. That's just arithmetic. I can throw it in a given bucket here for items. So there's a little bit of math hand waving that happens here, that this only really works if your hash value gives good distributions. Right? If every particular value hashes to 0, and I'm going to add all my items, I'm going to add Eric and Jeb and VV and Journey into bucket 0, I'm not going to get good performance. But assuming we can generate a hash value that is evenly distributed, which is a bit of a stretch sometimes, but in general, we can hash things with even distribution here, right? Then I can spread these out onto the buckets here, and I can instantly find what bucket it goes in. Now, there's some other hand waving we do in that we want to make sure we have enough buckets here based on our number of items. So if I want to throw 100 items into 5 buckets, I'm not going to get very good performance. So I'm going to have like 20 items in each bucket here, and that's not going to work super well, right? Not great. It'd be better if I have more buckets than I have items. So you get this idea of a load factor. Load factor. And again, really smart people have looked at this sort of stuff here. There's ideal load factors to get good distributions where you minimize the amount of duplicate or multiple items in buckets and things like that. But somewhere around 75% is probably fine. So what we're doing is we're going to store more empty spaces than we have items. So we're going to use up more memory so that adding stuff to my buckets and finding stuff in buckets is super fast. So if I've got 1,000 items and I want to be a load factor of like 75%, I'm going to have whatever 1,000 divided by 75 is. I picked a bad number here. 0.75. I'm going to have 1,300 buckets or so. So I'm going to have extra space, extra memory used with empty buckets just sitting waiting here. So that when you go and add something or try and find something here, I can instantly, in constant time, hash the key, go look in that bucket. Hash the key, go look in that bucket. So we can get performance here of O of 1. Right? It's a constant hash and calculate index, get the item from the bucket. Now, maybe there's 2 or 3 items in the bucket, but we're going to hand wave and say, mathematically there'll be a nice even distribution here, and 2 or 3 at most because we're maintaining a constant load factor doesn't impact an n, right? Because I will always have more spaces than I need here, right? So setting an item is constant. Right? Getting a particular item out is constant. So actually I did my buckets wrong here. So we should do, I want a list of lists. Oh my goodness.
In terms of the list, isn't, if you only have 11 spots there, isn't it gonna get full?
Yeah, so we're gonna need to resize eventually. So there is a resizing, and we'll do the same sort of geometric doubling so we can amortize that across as well. Yep. I'm trying to think of how do we make a list of lists here. My goodness. Wow. I cannot brain today with the Dayquil. Goodness. So sure. So for, I don't know, inner bucket in range 11, self.hashtable.append a list. I don't know. I can't think of anything right now, but this gives me, now I have 11 lists in my hash table. Okay, so now it's never none here, right? So this now will find me the list of items here, right? Because it will be a list. So that I can have, items or 4 items in my self.hashtable at the index. So figure out what bucket it goes in. Maybe we call this the bucket index. Let me rename this here. So refactor, rename, this will be my bucket index. So which bucket? And then for every item in that bucket, if now I need to compare them, if the items dot key is equal to the key, then I'm going to update. I'll say the old value is items.value and then items.value is the new value, and then I'm going to return the old value, right? Update it, if I find it. So compare the keys. If you find keys that match, update the associated value. If I've looped through and I haven't found one here, right, I didn't return, I'm going to take my bucket here, and I'm going to append an item, a new item, self.item, given the key and the value, right? So if there's something in the bucket, go see if the key matches. If I found the match here, update. If I didn't find the match, or if there's nothing in the bucket, right? If there's nothing in the bucket, if it's an empty list here, I just go and append.
Can you explain the last line, please?
So this is, if we didn't update a value, add a new key value pair. Right? So if we haven't found a key to update with a new value, right? This is set item. Set will add or update. So this is the I found something to update line here. This is the I didn't find anything to update, so we're going to add a new item. Add a new key value pair.
What is the self.hash table?
So our hash table, right, is this storage here. This is our list of buckets that we're dropping everything in, right? So this is I've got 5 buckets here. This is my hash table. And these are really just lists inside of it, right? It's a list of lists. Bucket is a little easier to conceptualize sometimes. Yeah, just a list of lists. So I can set the item. Now, at some point, now I need to be counting, right? So if I didn't add a new item, I don't have to count here, but if I added a new item, my self.number of items goes up by 1, right? And then if I hit a certain load factor, I have to resize this sucker, which takes a little bit of time, but we can do it here. So we'll say, hey, if my self.number of items divided by my the length of self.hash table, if that is greater than, and now let's just make a constant value here, because this is probably a little cleaner here. So we'll have load factor 0.75. So if that's greater than my load factor, or maximum load, maybe how about maximum load factor? So if I have more than 75% of my buckets with something in it, or maybe a bucket has 2 or 3 things, but essentially if I'm reaching where I want to be for my max capacity here, max load capacity, then I need to resize. So I'm going to call self.resize. Now I don't have a resize function. Oh, that should be private here too. So resize. Now resize is a little tricky here. So what we're going to do, similar to when we made lists bigger, right? We did this a while back here. So this would be self.define resize here. So I know I've got a hash table of a certain size. I'm just going to double it, right? Because again, I don't really know. There's better ways to do it. It has to do with prime numbers. It's fine. We're just going to double our size. At least doubling will be good. Probably like double and then the next prime, or really smart people looked at this. The reason why when you do this modulus, if you end up with like powers of 2 or factors of 10, this doesn't give you a very good uniform distribution. But if you modulus by a prime number, generally you're going to get a better uniform distribution. So it helps with that, making sure we don't have multiple things in the same bucket. That's all. For our purposes, we don't really care right now. All right, so we're going to resize. So I'm going to have a new bucket or new hash table. So I'll have a new hash table is a list, and then for bucket in range, I'm going to go 2 times the length of self.hash table. Right, we're just going to double. New hash table, append a new list. Right. So now I have double the number of buckets. Right? They're just lists here that I had before. Then I need to go through for every bucket in my current hash table, I have to put it in the new location, right? So I'm going to say now for bucket in self.hash table, for every bucket, then I'm going to say for every item, for item in bucket.
In terms of time complexity, how good is that?
So resizing is always going to be n-based. The more n I have, the longer this takes. But because we do this based on the geometric doubling, we only have to do it every so often, just like with our list-based stuff, so we can say on average it's still constant. Because if I don't have to double for the first 11, then I don't have to double for the next 22, and I don't have to double for the next 44, right? On average, it's still just 2 operations to add, right? because the bars fall down, essentially, in the picture. So for every item in the bucket, I have to find the new spot here.
So I'll just like reverse the next one. I'm both.
Yeah, no worries. No worries.
I don't like I'm both.
It's tough. It's tough. It helps if you're on Dayquil. It makes it make a lot more sense. All right, so we need to put the items in the new bucket. Right? So the new location for these things, then, I'm going to say my item then needs to go to this new bucket. So my new index is going to be the hash of the item key modulus the length of the new hash table. Right? Based on how many buckets I have, again, always use this hash function. It's a constant value here, modulus the length of the new table. That's the new index. And then my new hash table, at the index, append the item. The new index. Append the item. Now, I don't need to do any sort of checking to see if it already exists there, because I know I don't have duplicate keys. I can't have duplicate keys, so I don't need to do any of this work where I was like, oh, hey, if I found a matching key, go do something, because I won't, right? This only ever happens when we move stuff. So for every bucket, for every item, put that item in the new spot. Right? And then we're done, we'll say our self.hash table is equal to the new hash table.
Well, why exactly do you have a bunch of nested lists? I can choose the list, a bunch of them, right?
Yeah, so because we have this idea of buckets, right? If I didn't have buckets, if I had two values that hashed to the same number, what am I going to do? And the book will take you through the different things you can do. You can say, oh, we'll go to the next open bucket. That gets tedious then if you have to remove things. You have to know, did I remove the thing before? It's messy. So buckets is the best solution. Again, you can read through the textbook if you want to see all the other possible solutions. Seeing all the bad ones first might make this make a little bit more sense. I apologize. It just takes so much time to go through all the bad ones. Yeah, so that's all the pages I skipped over. This, excuse me. He's got it in here. Let's see. So there was hash codes. Hang on, where is it here? Separate chaining. So this is the buckets, essentially. If you want to be super fancy, you can do these as singly linked lists. I don't really care. Someone will tell me if it's faster or slower. Buckets are just easy for us. Essentially, they're buckets, right? So here's the first one, here's the next one, here's the next one, here's the next one. That's fine. Linear probing is saying, okay, if this bucket's full, go to the next one. If it's full, go to the next one. If it's full, go to the next one. This doesn't work very well because when you start deleting things, well, then you have to track whether or not it was available or not, and then it's just really messy. So that one's not great here for that one. So then we do load factors, rehashing, and efficiency here. So really cool. So for getting an item, O of 1, setting an item, O of 1, deleting an item, O of 1, length of O of 1. Iterable is still n because there's n items here, right? Our average time, right? The worst case, we know we have to do some resizing. That's fine. We'll just hand wave and pretend like it doesn't happen, essentially. But we use all the buckets here so that I can just keep, when I do get two values with the same hash, I can keep them in the same bucket without doing extra work. That's why it's a nested loop, sorry. That was a long story. This is the easiest solution for us, and it still performs very well. Yep. Okay, so if we need to resize, we'll resize. Great, go ahead and do that. That's for set item, right? So then for get item, right? If you, now really this, I want to call that the key here, for the key. I'm going to check to see where the index should be. So the index should be, now if I have the same code twice, I should feel bad about myself, right? The bucket index, length of the hash table. We'll fix this later. This is like one line. I feel a little bad, but that's okay. So I'm going to go find that bucket. Now for item in my self.hash table, at the bucket index, if the item.key is equal to the key, return item.value. Right? So for every item in that bucket, grab the value, or see if the key matches, return the matching value. If I haven't returned a matching value, I'm going to raise a key error. Hey, that key didn't exist. There was no key there, no value with that matching key, right? I didn't find it. And this is why hash values are so important, because if I try and calculate the hash value of an object, I need to be able to go find which bucket it should be in. So if you don't have that hash function here, like for assignment, and I go look at memory address, but these two quizzes should be the same, they're going to be at different locations. I won't get the right one back out. That's why when you have an equals function, we have to have the hash function for you to be able to use it in a dictionary. So that I can say, hey, these two are equivalent, they will compare as equals, right? If you say these two are equal, they have to have the same hash value because I need to go find it in the hash bucket, in the bucket based on the hash value, right? Without a hash function, you can't do that, right? Because first quiz and second quiz were based on their memory address. That's not helpful at all, right? Not going to work for us. So get item is pretty quick, right? This is always going to be constant time. O of 1, right? And again, there might be 2 or 3 things in the bucket, but we're going to say we have this nice uniform distribution here, 2 or 3 things at most, no matter the n size here, because we're keeping that load factor. I could have 100,000 items because my load factor still maybe 2 or 3 things in the bucket. Not too big of a deal. You know, in practice, you might end up with 10 things in the bucket, but again, generally it distributes relatively well, and that's part of our issue here. Now, you can do bad things, and Python will let you do bad things. So I could say, if I wanted here, return 0. I now have a valid hash function. Every single assignment will hash to the exact same bucket. Now, if I try and put these in a dictionary, I'm going to get terrible performance out because they all go to the same stinking bucket because I didn't give it a good hash function here, right? So just because you can do it isn't, you know, this is terrible. Terrible. They will all end in the same bucket. Just like you can make a binary tree that's, you know, a right child, 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 and have n items in a chain, you can do that with our hash maps as well. You can do bad things with it, depending on what you want to do here. So we won't do that one. We'll leave it as the good return. Now, excuse me. When we do hash values, though, we need to make sure that these values won't change. So this is technically a little bit bad here because I might be able to change the score on the assignment here. So if I put something in a bucket and then I change the value of the score and I try and get it back out again, and I'm generating a hash value off of the score that was changed, is it going to find it in the bucket it was in before? No, because the value has changed. So the rule with hash values have to be based on immutable properties only. Immutable? Is that 1M? Immutable? Immutable? How do you spell this thing?
What if you have to change the score of the quiz?
So then when I go to hash it, I'll get a different hash number and it's going to look in a different bucket. And it won't find that quiz anymore. So this is actually probably bad here, right? We probably want to say, hey, just do the hash of the name and maybe make this thing private. So it doesn't change, right? Once it's quiz 1, it's always quiz 1. If you want to change the score, sure. I mean, it depends on what we want to do here, right? So this will make sure that if you want to change the score does change, we can still find it in the map, in the dictionary, right? That's really important. So making sure we have a consistent hash on immutable properties only. If the property doesn't change, it might be hashable. Now, this means I might have 2 different quiz 1s. One was a score 10, one was a score 5. That's okay if they have the same hash value because I'm still going to check equals. Right? When I go to that bucket and say, okay, this is for quiz 1, you had a score of 5, I'm looking for one with a score of 10, I will find that one eventually because I'm checking equals. This was what I was saying here. When you hash, equivalent objects have to have the same hash, but just because you have the same hash doesn't mean you have to be equivalent objects, equal objects. Right? So I can have 10 different assignments all with the same name, as long as they have different scores, that's fine. Again, performance-wise, it might suck, because I've put them all in the same bucket. But, you know, we're going to hand wave and say, generally, we'll have some uniform distribution here. If you make 10 quiz 1s and put them all in one dictionary, that's on you. You just did a bad thing. I think this is why we kind of build these and work with these to understand what's fast and what's slow, right? Why we might not want to do that sort of thing and not get the performance we're expecting out. Oh, I forgot to take more insulin. Sorry, one sec. Let's make that 5. My smart pancreas is almost as good as your pancreas. It's just like a 20-minute delay. Okay, so we can get stuff out here. Now to delete an item, right? We can add our delete item. Define delete item, given a key. Same idea here. But now if we find the key, we're not going to return the value right away, right? We're just going to go and delete it. I think we'll return it eventually. It's maybe we'll keep the old value, item.value.
In case you want to just change the score, why don't you just delete the previous one and add a new hash with the new score?
You could. Yeah, you could do that. Knowing that you have to do that is a little bit obnoxious though. Right? I don't think you would expect, hey, if I want to keep this thing in the dictionary, that I'd have to go delete the old one just to update. Generally, updates just kind of work for us. So it adds a little bit more chance that we could screw it up.
Okay.
Right? And just like our end users, us programmers are going to screw things up all the time too. Right? You know, it's going to let us try it, and then it won't behave like we expect, and we're going to spend 2 hours debugging it. Like, why is it not working? Oh, we forgot we had to go update this first or delete it first. So trying to keep it as simple as possible for us, to make it less likely for mistakes is generally a good philosophy there. Yep. All right, so we'll get the value. Now I'm going to go delete that one. Now, I can't delete I guess I can delete while I'm iterating it here. So I'm going to take my, oh goodness, so I have to, it's an item, right? So I have to delete an item out. An item has an equals, so I have to make a new item. Okay. So make an item to delete, equals a self.item, given the key and the value. I guess the value doesn't, yeah, the value doesn't matter. It's just the key here. And then I can call dot remove item to delete. Does remove, I don't think remove returns anything, does it? Yeah, it just removes it. Okay, and then we can return the value. Right, because we're keeping keys in here, or I'm sorry, items in here, I have to make an item so I can remove the matching item. Right? We wrote that item class that matches. Right? I don't just have tuples. It might have been easier to just use tuples, but I think this way I can use the equals, not equals operations here, and less than, which is fun. So we can sort these things if you wanted. Okay. So to delete an item, right? Go through, if we have a matching key, get the value out, go remove it from the bucket, and then return that value. If we didn't remove anything, we have a key error. Right? So get, set, and...
So how do you know what the key is?
So they tell me. So like you would say delete, you know, Eric out of the dictionary. Right? This is O of 1 as well.
Why is it better than the built-in list thing Python?
The Python dictionary?
Yeah.
It's
Python
not.
dictionary.
No, the Python dictionary is better than ours. But
Oh.
just like you could use the stack and the queue and the list, like in the Python, we're looking at how they're built to understand their performance better. Right? That sort of thing. I imagine engineers probably build engines. What?
But the built-in one is better.
Yeah.
I'm sorry to cut you off, what would you say?
No, so the built-in one's better, yeah. So I imagine like our engineering friends build engines for cars, so they know how they work, right? And they've gone through the process. Not every engineer will always build an engine, but like if you've gone through the process, you understand a little bit better, you know, why your component does its thing. I imagine. That's my guess. I never studied engineering, so, or the physical engineering sciences.
In terms of the queues and stacks, are there built-in queues and stacks from Python?
Yeah, remember, so we looked at, I think they were all based, was it the deck? I think is what they were mostly using. Python built-in queue class. What do they have here? Geeks for geeks. What do you have here? Yeah, I think it was all using deck from collections as the deck class. I think mostly that was the one that was the built-in one for that. Yep. All right. So for hash maps, then we can get the length here. Yeah, we need to have length. So the length of our self. Define length. We'll just return self.number of items. Oh, when you delete something too, right? We need to take our self.number of items -1. There we go. Right. Getting doesn't change anything. So remove an item. Great. Number of items here, and then the iterator here. So if I want to iterate over each item here. And this is why in dictionaries you don't get the same order back out. We're just going to say for every bucket, here's every item, right? So I can define my, I might probably have to copy his iterator code here because I don't remember. Let's see, iterator. Yeah, this is the chain hash map, sure, whatever. Linear, we don't want a linear probe. Yeah, yield table key. Okay, so something like this here. You can probably copy something like that. Why does he use such terrible variable names? These are awful. Index and range length of self.hash table for item. This is the bucket index, right? I'm just trying to name these things nicely here. So for item in self.hash table at the bucket index, the yield, is it yield return? Yield the item.key. Right? So grab every bucket, starting at the first bucket, grab every item out and give that back. So just because you put them in order, you know, Eric, Jeb, Vivi, doesn't mean you're going to get them back out in that order because it's based on their hash value. Right? And this is why we don't have a guaranteed order header here. There we go, 2 underscores. Shoot.
What does yield do here?
Yield says give this item back and then sit and wait. Remember where you are, so that when you ask for the next item, the code just keeps on running and keeps on running. So we did this way back when we did our geometric stuff here. Remember? Where's it here?
Oh, because it goes like
Progressions.
year and next, right?
Yep. We did our progressions here. We did the yielding here. So we just said, hey, here's the next value. So Python behind the scenes tracks where it is here, which is super cool. As you ask for the next one, here's we did it in, oh my goodness. Is this that's vector? We don't want vector. Stop here. This iterator here was just giving back the next value essentially for our sequence. We didn't get super deep into the iterator here, but if you have a next function, it gives you the next one. So we're skipping the next piece here. So, oh, we didn't use yield, I'm sorry. So yeah, yields this, we did it in one of these, I thought. But essentially it will remain here waiting for you to call for the next one. So I can use it in a loop. So now I can say, you know, for item in my hash map, your gradebook hash map or something. Now, because I have an iterator down here, right? Custom book for item in custom book, print item, right? And that should give me each key out here as we go. So I should be able to do all of these here. Eric, Jeb, right? Same idea with these ones here, just like a dictionary. Oh, and now, yep, so I get them back out, I got Jeb first, Jeb and then Eric, because it hashed whatever JPB came up before mine. Sure, whatever it was. All right, we're actually doing pretty good. We're doing pretty good. Let's see, where did that end up here then? Our hash table. Yeah, with our efficiency here, get items, set items, good. Bucket get item, bucket set item, bucket delete item, sure, our iterator. Yeah, so sure, capacity is 11 and P, whatever. So they use this whatever version here, which works out really nice, which is fine. So hash times your scale plus your shift, modulus the prime, modulus, sure, it's a little faster, right? We're not gonna bother with it, okay? Apologies for not going super deep. It's not worth the time right now. Setting the item, making sure we have the right length here. Okay, so they're keeping the load factor at half. Sure, that's fine. We'll resize, you can delete an item, resize an item, sure. You don't need to do the separate chaining or linear probing. Okay, awesome. Yeah, we actually got really far. That was fun. A little fast, I'm sorry. I'm still a little fuzzy right now. Yeah, that's our hash tables. So we don't actually have a whole lot to do for Thursday. Because we're not really going to get into skip lists at all. We don't need to deal with the sorted ones because we're going to get into sorting later as we go. So I think we'll just have time on Thursday then to work on the project, our last stacks and queues project. So I won't plan on a lecture. I'll probably hang out at my office because I still have my Thursday night class. But I'll hang out over there if you want to chat about the project. We can come work over there on Thursday. Sound good?
Yeah. On
right.
Thursday, possible if we still have time to do it. Would you mind going over a couple of topics again?
Yeah, definitely. We can do like a little catch up time.
Yeah.
Yeah, for sure. Probably I'll put a note in Canvas. I'll just be hanging in my office on Thursday then. All right. Thanks, y'all.